This video brings us to our second rule for simplifying a square root, and that is that you can never leave a square root in the denominator of a fraction. So you can see here, I truly have a square root. This square root or radical is going over the entire fraction, and so you could think of this fraction as the square root of 4 over the square root of 3. This one here has a radical in the denominator, so it would also be considered illegal and not simplified, and you can't leave it there. The reason for that is going along with the idea of a rational number. You cannot have an irrational number in your denominator. And so we make it a rational number. So our first property, which you see below, is our division property of square roots. And that is the one that says that you can separate the top and the bottom into their very own radicals. So when you have a problem like the square root of 13 over the square root of 64, it makes sense to separate them because that 64 is a perfect square. And so I can remove the radical by taking the perfect square, or the square root of 64, which is just 8, and now you have no radical in the denominator, and still you need to check that you have no perfect square under the radical in your numerator, so you're good and you are simplified. Over here it's the same idea. You can square root the 120 and then you can square root the 4 separately. However, this square root of 4 will take care of itself, but 120 has a perfect square factor in there. And so you want to simplify the numerator as well. And so you need to find a factor, the largest perfect square you can, that goes into 120, and I am going to pick 4, even though I'm probably wrong there. So I'm going to take and rewrite this as, the square root of 4 times 30 all over 2. Now this is just me starting to factor the numerator, and that was me simplifying the denominator. Now I can take the 4 out, and I'm going to have 2 times the square root of 30 over 2, and these cancel. And I still need to do one more check and make sure I don't have a perfect square factor of 30, and I would only have like a 2 and a 15, and that won't ever give me 2 of anything or a perfect square. So I am done at the square root of 30. But now that I'm looking at this problem here, I could have done it another way as well, and that would be to take the 120 and divide it by the 4 right away, and then you end up with your 30 as well, which might have been a faster way to do it. So you can divide if you need to or want to, and you see that you get the same answer no matter which route you take in solving it. Well, we jump right to complicated ones again, and this whole video is on division properties and how to remove radicals from the denominator. So the first thing I would do in looking at this is try to figure out what's going on with these numbers. 75 is not a perfect square, and so my next step would be to try to take 300 and divide it by 75, and thankfully that is a 4, which I'll later take out of that radical. Then I would look at my exponent properties. I have powers with the same base, so you should remember that you can take the exponents and subtract them. So 3 minus 1 is x squared. Then I have y to the first power, remember that's a 1 right there, over y to the third power, so if I subtracted those, I would get y to the negative 2. And z to the fourth is just going to stay up top. Alright, your next step could be to start simplifying some things. My 4 can come out of that radical, my x squared can come out of that radical, my y to the negative 2 needs to go downstairs, and I'll deal with that z in a little bit. I don't want to take too many steps. So I have 2 and an x that's coming from square rooting those. And right now I'm at z to the fourth, and I'll put my y squared downstairs. Now z to the fourth is just made up of 2 factors of z squared. So maybe you see where that's going, and I'm going to make this its own radical downstairs of y squared. So really this whole thing is just a ginormic perfect square. So I will have 2x here, I will have 1z come out of here, and another factor, or z, come out of there. So I'm going to have a z squared outside, and then this y squared, the square root of y squared, is just y. And here is your final result. Again, there's a few different ways to go about solving these. The main thing is that you just keep reducing and simplifying until those two things happen. You have no perfect square factors under a radical and no square root in the denominator, both of which are true for this problem. I will do the first problem with you and then let you do the second problem on this slide. So seeing that I have 120 over 10 and the fact that that is not a perfect square, my next hope would be that I could divide these numbers. Thankfully I can. So you don't have to make this too complicated. It's just the square root of 12. Then you can do what we've done before, break that up into its perfect square factor of 4 times 3, and the square root of 4 is 2, leaving the 3 under the radical. So that's as far as you can go with that. Looking at the next one, you may have a bit of a problem with these numbers. See if you can reduce this fraction and if you can get a perfect square out of there. And I think you'll be able to, so go ahead and give it a try, and again, just reduce that fraction and you should see what happens. Pause the video now. And that is what your final result should look like. Again, there's other ways of getting there. As long as you ended up with that, you're probably doing something right. So we're going to look at this example because the situation will happen when you don't have a perfect square in the denominator. Here you do, and so it's easy to simplify this by those two rules and end up with the square root of 13/8. The problem is over here, the square root of 5 is not a perfect square, and so how do we get that rational radical out of the denominator? And the way we do that is by what is called rationalizing the denominator. What we're going to do is we're going to take a number that is irrational. If you did this on your calculator, you would get a decimal that is not repeating and not ending. But we can make that or turn it into a rational number. And the concept is actually kind of cool. Instead of making it the square root of 5, what could I multiply that by in order to make it a perfect square? And the fact of the matter is, if I could multiply this by another square root of 5, this denominator would become the square root of 25. And that's a perfect square and can be undone. Now you are allowed to multiply this denominator by the square root of 5 as long as you multiply the numerator by the square root of 5. This fraction here, the square root of 5 over the square root of 5, is just a 1. And you should remember that multiplying anything by a 1 does not fundamentally change it. So we are allowed to write that. Alright, so then we still need to multiply the numerator, so we get 2 times the square root of 5 in the numerator. And now 25, once you square root it, becomes 5. So that's why we say we've rationalized the denominator. That is a rational number. And nothing else is going on here as far as our two rules. Remember, those are no perfect square factors under the radical and no radical in the denominator. So I have simplified this fraction. I'm going to add another problem to this page before we do the one with variables, just because we're still new at this. So if you saw the problem 3 over the square root of 3, you would see that it's breaking the second rule of having a radical in the denominator. So again, we turn our irrational number into a rational number by multiplying by itself, basically, because the square root of 3 times the square root of 3 gives us the square root of 9, and I can undo that. And then I need to do it to the numerator as well, so that I'm not fundamentally changing the problem. And now we would just clean it up and get the square root of 9 on the bottom, which is 3. And these two do cancel, so if you ever can reduce or cancel, you should. Alright, let's move over to the one with a variable in the denominator, and this is really exactly the same. I have an a that's under a radical in the denominator, and I need it to go away, so we're going to rationalize that denominator by multiplying it by the square root of a in the denominator and doing the same thing to the numerator. Multiplying the numerator across, you get the square root of 3a. And then multiplying the denominator across, you get the square root of a squared. The square root of a squared is just a, and so now you have satisfied your two conditions: no perfect square under the radical and no radical in the denominator. The second example here is a little trickier in that I have a to the 5th power. And you could multiply by a to the 5th power, but you're going to end up reducing up top. Or you could be very logical and think, I only need groups of 2. So what could I multiply a to the 5th by to give me 3 groups of 2? And that would be the square root of a. And I'll explain it a little bit more. Just think about what I have in the denominator now. In my numerator, I have 2 times the square root of a, but in my denominator, I have a to the 6th power, because here I have 5 factors of a, and here I have 1 more, so I have 6 factors of a. And that could be written out, if you needed to, as a squared times a squared times a squared, all under that same square root. So all these can be undone by that square root, and you end up with 2 times the square root of a on top, and then a times a times a in the denominator coming from these 3. And you could clean it up further. Now this one can be done several ways, so come see me if this way confused you, and I'll show you just another technique. It's not really that different, it's just changing, it's just a little different. Alright, now we're at some big dogs here because these look quite complicated. And so we just need to start chipping away and attacking these things, trying to reduce them. And so when I look at this here, I can see that I could divide my 3 and 15 both by a factor of 3, and I'll do that. And you could still subtract these or cancel them, however you look at it. And so this starts off as, I'll do it down here, dividing them both by 3, I get an x in the numerator and a 3x cubed still in my denominator, both under radicals. If I wanted to subtract my x's, I have 1 minus 3, so that would be x to the negative 2 power, still under a radical, and my square root of 3 down here. And you should all remember your exponent rules, that you cannot have a negative exponent, and so that x is going to come downstairs and join my square root of 3. Now upstairs in its place will be the placeholder 1. And this is currently what you have. Now we have a radical in our denominator, which can't happen. However, I do have a perfect square under that, so I could bring that out right away. I'll put it out front. You just have a 1 times x coming from the square root of x squared, and then this is still here. And then you need to rationalize your denominator. You can't leave that square root of 3 there. And so I will multiply the top and the bottom by the square root of 3. So your final answer for this one, I will put back up top, is the square root of 3 coming from this multiplication up here. And downstairs I have x times the square root of 9. And the square root of 9 is 3. And there's my x. I feel like I went a little fast on that, so again, if I did and you have questions, just find me. The second one, I see that 9 under that square root and it bothers me, so I want to get it out of there right away. So I will. So I have 3, which is the square root of 9 times b, and my 3's cancel, so now this is becoming a nicer looking problem already. You just can't have that square root of b in the denominator, so I will multiply numerator and denominator by a factor of b, and then clean it up. So you will have the square root of 2b in the numerator, and then b squared, square rooted, is just b. And this is as far as you can go with that, and you're done. Again, the more you practice these, the better you'll get at it, and it's a super important skill. You will be doing this simplifying of radicals in geometry, and you will also do it in Algebra 2 and your math classes beyond. So this is not a one-shot lesson. This might be the first time you've seen it, but it won't be the last. Thanks for watching.